Welcome to The Explainer. Today, we're zeroing in on hops. Now, most people just know them as the ingredient that makes beer bitter, right? But chemically speaking, they are a profoundly complex, multifunctional powerhouse. Honestly, their true scientific depth is wildly underappreciated, even by working professionals in the industry. So today, we're doing a strict, rigorous, deep dive into the provided brewing literature. We're going to pull the exact mechanistic and technical data straight from these sources, and here's the catch. We're drawing a hard line. Zero outside assumptions. If it's in the text, we unpack it. If it's not, we explicitly call out its absence. Let's dive in.
Okay, so here's the roadmap for our analysis today. 1. Chemistry of hop bitterness. 2. Hop processing technologies. 3. Storage and degradation. 4. Hop utilization dynamics. 5. Missing scientific domains. And finally, 6. Summary and future directions.
Section 1. Jumping straight into the chemistry of hop bitterness.
So, botanically speaking, the hop plant develops these bitter resins and essential oils specifically around the seeds of the cone, which is the fruit of the plant. If you actually break open a whole hop cone, you'll see it as this distinct yellow powder. Now, historically, way before modern flavor profiles were the main event, hopping actually blew up in popularity because this exact yellow powder possesses potent antiseptic properties. It's this specific anatomy that literally houses all the brewing value.
A totally fundamental chemical transformation happens once you hit the brewhouse. The main resin we're looking at is called alpha acid. But when you expose that alpha acid to the intense heat of the boiling process, it actually undergoes a structural change. It isomerizes into, you guessed it, isomerized alpha acid. And this new isomerized form is a completely different beast. It's far more bitter, it's significantly more soluble in liquid, and crucially, it's highly stable. That stability is what allows it to actually survive all the way into the finished product. Let's talk about the specific thermal dynamics of that kettle boil, because they follow some pretty precise timelines. Believe it or not, over 90% of wort bitterness from that isomerization process happens within just the first 30 minutes of boiling. But if you want complete extractable bitterness, you're going to need about 60 to 70 minutes. Also, the isomerization rate is directly tied to temperature. It's a simple rule. Higher temperatures equal much faster isomerization. But, there's always a trade-off. While boiling is great for extracting those resins, the aromatic hop oils are incredibly volatile. In fact, most of those hop oil volatiles are completely lost during just the first 20 minutes of a boil.
Moving right along to Section 2, let's look at hop processing technologies.
Traditional brewing obviously relies heavily on whole hop cones, but honestly, there are some massive physical limitations there. Whole hops have incredibly low density, they are super bulky, and they retain absolutely all of their vegetable matter. That makes brewhouse handling a nightmare and transport ridiculously expensive. Now contrast that with extracts. By dissolving the alpha acids in either liquid carbon dioxide or ethanol, processors can actually concentrate the resins to standard alpha acid values, like 30% for example. This entirely eliminates the vegetable matter and means the product occupies just a fraction of the physical space.
So what advanced processing formats are out there to optimize all this? Well, first, we have Type 45 and Type 90 pellets. These are milled and compressed, with the vegetable matter completely removed to really concentrate those resins. Then we get into isomerized pellets and extracts. These are actually pre-processed in specialized plants, meaning the isomerization, which remember usually requires that long kettle boil, is already done before the brewer even touches them. Talk about a time saver. We also have reduced extracts, specifically something called tetra. And finally, pure hop oils or emulsions, which are just distilled aromatics used to impart hop character without adding any bitterness whatsoever.
I want to double-click on that reduced extract, tetrahydroisoalpha acid, or tetra, because its chemical utility is absolutely brilliant. We all know ultraviolet light easily penetrates clear or green glass bottles. Well, if normal isoalpha acids are exposed to that UV sunlight, a chemical reaction kicks off that produces that notorious skunky or light-struck flavor. But by using the reduced tetra form post-fermentation, the beer is completely protected from this UV reaction. Plus, as a heavily documented bonus, beers treated with tetra actually show enhanced foam stability. It's a total win-win.
Okay, Section 3. We need to talk about storage and degradation.
The degradation pathways outlined in our text are honestly pretty stark. Whole hops are incredibly vulnerable to entrained air, which degrades their hop resins rapidly. And since vacuum packing giant bales of whole cones just isn't practical, they strictly demand costly refrigeration. Hop pellets, on the other hand, deteriorate much more slowly, precisely because they can be easily vacuum packed or sealed in an inert gas environment. But if you're looking for ultimate stability, that comes from hop extracts. CO2 or ethanol hop extracts essentially do not deteriorate at all as they age. They are literally immortal in the cellar.
All right, Section 4, Hop Utilization Dynamics.
So hop utilization is basically defined as a metric of efficiency. It's comparing the raw amount of alpha acid you added to the wort versus the actual measured bitterness you end up with in the final product, measured in IBUs. Now, there is a totally fascinating discrepancy explicitly laid out in our source literature. The text states that 1 international bitterness unit, or IBU, is generally assumed to equal 1 milligram of iso-alpha acid per liter. But then it immediately notes that the isomerized alpha acid actually only contributes about 0.7 units per milligram per liter. The balance is essentially made up by other bittering compounds like beta acids. We're just presenting both of these documented positions exactly as the literature does, without trying to resolve them here.
The physical parameters in the brewhouse heavily dictate this isomerization efficiency. First off, timing is absolutely huge. Less contact time simply equals lower utilization. To put it in perspective, a short 5-minute boil yields a tiny 8% utilization, while a full 60-minute boil bumps that up to about 30%. Wort pH is another massive factor. A higher, more alkaline pH significantly increases both the isomerization rate and solubility, but you also bleed efficiency through things like trub absorption, where heavy volumes of protein and carbohydrate literally drag the bitterness out of solution. Yeast adsorption also plays a big role, heavily dependent on yeast growth during fermentation. And finally, if you're starting with a high specific gravity wort or a really high concentration of alpha acids right out of the gate, your overall utilization efficiency is going to take a hit.
As you'd expect, how the hop is processed has a colossal impact on these utilization numbers. Look at traditional whole hops and standard pellets. They only achieve about 25 to 30% typical utilization in the kettle. But watch what happens when you switch to isomerized pellets or kettle extract. Efficiency instantly doubles to 50 or 60%. And it gets better. If you use an isomerized post-fermentation extract, you're bypassing all those brewhouse losses entirely, and utilization absolutely skyrockets to between 70 and 85%.
Let's actually walk through a quick mathematical example straight from the text to see how this plays out in reality. Imagine you've got a 500 hectoliter batch, and your target is exactly 35 IBUs. If we assume 1 IBU equals 1 milligram per liter, you're going to need 1.75 million milligrams of alpha acid in your final beer. Now, if your hops contain 8% alpha acid, and you magically had 100% perfect conversion, you'd only need exactly 21.9 kilograms of hops. Easy, right? Well, reality check. Because of all those utilization dynamics we just covered, you're probably only expecting a 30% efficiency rate. So you have to adjust that final weight. You actually need 72.9 kilograms of raw hops just to hit that same 35 IBU target. These physical losses literally dictate your entire recipe calculation.
Moving into Section 5, let's look at the missing scientific domains.
Now, to maintain the absolute academic integrity of this explainer, we have to boldly acknowledge the strict limits of the literature we've been provided. We can't just go filling in the blanks with our own outside knowledge. As the text itself demonstrates, the documentation provides amazing detail on essential kettle dynamics, but it remains completely silent on several highly advanced domains of modern hop chemistry and agronomy.
Clinically speaking, here's exactly what is entirely absent from the source material. We see zero mention of botanical taxonomy or terpene biosynthesis pathways. These specific molecular structures of humulone, cohumulone, and adhumulone, completely missing. The text utterly omits the different classes of hop polyphenols, tannin-protein interactions, and bioactive flavonoids like xanthohumol. And while it does briefly mention antiseptic properties, it fails to detail the actual antimicrobial mechanisms against gram-positive bacteria. Furthermore, if you're looking for modern topics like essential oil biotransformation by yeast, the actual mechanics behind dry hopping haze, thioprecursors, or even how terroir and the hop storage index affect agronomics, well, you're simply not going to find them in this specific text.
And finally, Section 6, Summary and Future Directions. So, tying it all together, based strictly on the literature we've reviewed today, the core technical takeaway is this. Hop functionality in the brewhouse is primarily a function of the thermal degradation and isomerization of alpha acids. But this chemical reaction is in a constant tug-of-war against significant utilization losses driven by physical parameters, things like boil time, pH, trub, and yeast absorption. Ultimately, all those processing formats we discussed, from pellets to liquid CO2 extracts, exist primarily as tools to manipulate these exact efficiency numbers and lock in stability.
Which leaves us with this final, incredibly provocative thought. If pre-isomerized extracts can already push our mechanical utilization all the way up to 85%? How might integrating all that missing research on things like yeast biotransformation, thiol precursors, and complex polyphenol interactions completely redefine modern brewing mathematics? It's a huge, fascinating gap in the literature we reviewed today, and absolutely an essential frontier for future exploration. Thank you so much for joining me for this explainer. See you next time.